Okay, good.
Right, yes, the next talk is by Mischa Woods on the resource of control in quantum thermodynamics.
Yeah. Okay. So thanks for the introduction. So this is I'm Mischa Woods. I'm a postdoc at ETH in Zurich. This is joint work with Michał Woods, who is in Gdansk in Poland. So okay, I just start with the laid-back motivational introduction. So in macroscopic thermodynamics, we can be interested in processes, for example, in pushing in a piston. So this requires some manipulation of the system, and more generally, you could think that we do these kind of manipulations in many sequences to make machines. A typical example could be some cycles of a heat engine. So, and in macroscopic thermodynamics, we care that in every between every equilibrium of the cycle, that the second law is satisfied, so that the free energy is non-increasing. This is all very good, but it doesn't say anything about any potential costs from a thermodynamic viewpoint of any kind of control in these manipulations. Having said this, we have thermodynamic autonomous machines which work. So clearly somehow these costs of manipulating the system can be neglectable. Okay. Because, for example, here I've drawn a steam engine. So if you have this steam engine and you just had your thermal baths set at the right temperatures and are large enough, you could, in principle, you could just let this thing go and it would run autonomously. You wouldn't have to keep manipulating it consistently. Okay. So now in quantum thermodynamics, roughly speaking, you can say that the field it's kind of divided into two camps, more or less. So on the one hand, there's the many-body / mass equation approach, and then on the other hand, there's this quantum information / resource theory approach. And these communities tend to be quite separate. Like, for example, here we have people from the quantum information resource theory camp, but not really people from the other camp. Yet there are some differences. For example, in here, normally they start with some large many-body system, and they can then derive a mass equation, and then everything is really autonomous. For example, we have these absorption refrigerators or absorption heat engines, which really run autonomously. You can just have the initial time-dependent Hamiltonian, and it will just run over the bath and do its stuff. On the other hand, in quantum resource theory, the systems we consider tend to be non-autonomous because we have to apply these CPT maps to the quantum systems, which involves you can always think of these in terms of applying some unitary over some larger system. So at the end of the day, we have to apply these unitaries. And this is a bit reminiscent to, say, in quantum computation in the circuit model where we have to apply gates at different steps in the process. There are many different examples of machines. For example, one machine is this heat engine, which in the camp on the left, they can achieve some heat engines where the standard deviation, the work extracted, grows as the square root of the mean work they've extracted. On the other hand, there are also machines that run as heat engines which can do better. They can work at the same efficiency but have an arbitrarily small standard deviation of the work they extract. But again, these are non-autonomous on the left, whereas the ones on the right are autonomous. Because on the ones on the right, you have to apply different unitaries at different stages. So now I'm just going to talk what I mean by this application of unitaries being non-autonomous. So one way to think of this is the following. You can imagine what we do when we say apply unitary is that we have some quantum system and it's in some state rho A for all times t before some time t1, at time t1 we say, okay, we now apply, we start applying the unitary such that at some later time t2, it's now in this latter state here, and it stays in that state for all time t greater than t2, okay, or until you apply some new unitary. Another way to phrase this is like this, where we can see now, we can write it as some time-dependent Hamiltonian acting on the system, where this time-dependent Hamiltonian is just given by this expression here, where this is some integral over some, say, hat function, okay, which is 0 before for the time before you want to apply the unitary, and is also 0 for the time after you want the unitary to have been applied. So so this, as I say, it's a time-dependent Hamiltonian. So what does that mean? It means that this system, you have to have someone externally changing the Hamiltonian at different times in order to realize this. Okay, but why? But then in the resource theory approach to quantum thermodynamics, we assume these unitaries are thermodynamic free. And of course, the reason for that is simply because they preserve the entropy, because entropy is invariant under unitary transformations, and also, at least if you demand the energy preserving, then of course they don't change the energy. So, and these are the two thermodynamic quantities that we kind of care about. So that's good. So that they're free, but they're not autonomous. So then a kind of interesting question is, can we make this unitary autonomous and free at the same time? And if we do so, then we can, in some sense, we can put these two camps on a similar footing of these two different approaches to quantum thermodynamics. Okay, so in other words, as I say, you think of the green dots representing the quantum system we want to apply unitary to, and the standard approach at the moment is to simply neglect the control system. Okay, so now we just consider the system of interest. So what we will do in this talk is we want to consider that model, but we're going to consider a model where we have some ancillary system, which I'll denote generically with a underscript C in this talk, and a time-independent Hamiltonian over the system of interest where we want to apply the unitary and this control device of this form here, where explicitly this Hamiltonian has to be time-independent, and in such a way that the desire is that when we trace out or neglect this ancillary system, that we've really applied this this unitary to this system, okay, between times t1 and t2. Okay, and moreover, we'll be also in this talk we'll be interested in a very well-known and based, if you want, paradigm within this quantum resource theory, which is so there are two versions. I'll start the first version and then the second version. So the simplest version is what's known as thermal operations, where basically you can think of it as having thermal baths and allowing to throw away systems. So specifically, and we've heard about this already a few times during this conference. So we say that a transformation from on the system between a state rho 0 to a state rho 1 is possible if there exists some thermal state in a Gibbs state, and an energy preserving unitary over the system and the Hamiltonian of the Gibbs state, such that when we apply this unitary and disregard the thermal state, then we get the state of interest. Okay, and clearly this is a very thermodynamic setting. We have these free operations and we have thermal states. So that people have built on from this and extended this protocol to a slightly more general setting, which is known as catalytic thermal operations, where in addition to these other systems we allow for a catalyst. And by that I mean that we have the same conditions as before, but in addition we now say there has to exist another system with some we would call the catalyst system, such that now when we apply these thermal operations on both the initial state system and the catalyst and trace out the the thermal state, that we get the final state of the system tensor producted with the initial state of the catalyst. And the reason why we consider these to be thermodynamic free is because if you see that the state of the catalyst is returned after the operation to the initial state. So there's no thermodynamic cost in the sense that if you prepare it once, you can reuse it again and again forever. Now there's an advantage to these operations because it turns out that there are some operations which are possible via the latter scheme, via catalytic thermal operations, but are impossible without the catalyst, with simply thermal operations. So this is a non-trivial extension to the theory. Okay, so now we're going to think about how we could actually represent this from a time-independent, autonomous system. So first off, within the model I just discussed, we want this rho A system to be the system of interest, the catalyst, and the thermal bath. And now we consider what would happen if control were perfect. Okay, so if control were perfect, then we could do everything perfectly with a time-independent Hamiltonian. What we'll get is something like this. So for all times before we decided to apply the unitary, the system would that we want to control, well, nothing would have happened. It simply will be the state as if we hadn't done any control, and the control device would be evolving according to some free Hamiltonian without having interacted. Okay, and then after and there'll be some time when the interaction is done, and then after the unitary is applied, and some time of interest T3, then if we trace out the bath, what we would also like in the ideal world is that the final state of the system has been it's gone to the final state. The catalyst is exactly the same as the initial state, and the state of the control device is, again, it's just its free evolution, as if nothing had happened. So you see that if we see in the ideal case what we would want to be able to achieve is that now we can see this system C plays a dual role. So on the one hand, as we've discussed, it has the role of being of the control, in the sense that it has some time-dependent Hamiltonian, it's somehow applying these unitaries. And on the second, which is the important one maybe for if you want to know how to analyze this from a thermodynamic viewpoint, is that you can see it's exactly like a catalyst, in the sense that, or we could say like a dynamic catalyst, in the sense that after the transformation, it's in the same state had we not interacted with it. Okay, so it's like you have to slightly generalize your notion of catalysis here, but it's the same thing in the sense that nothing has degraded, because had we not used it, we just waited that time and it would have been in this state. So we can see it in the ideal world as simply as catalysis. And also another notion as well that's important, is interesting here, is we can also view it in some sense as a clock. Because if you see what's happening here, the full dynamics over the whole thing has a time-independent Hamiltonian, yet if we trace out this clock or control system, then now the system has changed in a very particular way at a very particular time. So somehow this auxiliary system has to have some internal notion of time. So it's also useful to think of it as a clock. Okay, but of course the world is not ideal, so in reality what's going to happen with the system is that even before we wanted to apply this unitary, that the whole thing with time-dependent Hamiltonian will be some generic maybe correlated state which is correlated, so it's not product, and similarly after the time the unitary has been applied, it will also be some correlated state which is also not product. So so now what we can say is that what's more, generally speaking, the reduced state on the control system will not be equal to that of the free dynamics of the clock, because it would have suffered maybe some back reaction or something. So the distance in the ideal case and what we achieve will be some non-zero epsilon. So now what you see is that actually, what actually happens is that we can think of this as some inexact catalysis. And not only that we can think of control as inexact catalysis in the real world, is that you may think at this stage, well, okay, but why am I giving this talk? What's the problem here? Because clearly, as I make this system very, very large, the dimension very large, maybe I allow it to have more and more energy, I will be able to make this epsilon go to 0. I mean, surely that should be the case. And as you write, yes, it is the case, so that's not an issue. But the problem with inexact catalysis is that it's a very tricky thing, and there are other potential issues that can happen. To illustrate my point, I'll just talk. I'll give an example of what's known about one example of inexact catalysis that's known in the literature. So this is I mean, there are previous results too, but I'll just concentrate on a result by Nelly Ng and co-authors from 2015, because it's of particular relevance to illustrate the potential issues here. So as I said, so inexact catalysis can be thought, or in the context of thermal operations, can be thought of the following process. So we have some initial states with some catalyst, and it goes to the final state of interest, but the catalyst is not perfectly returned to initial state, but it's returned to it goes to some state sigma prime. For this particular example, now consider the case where the thermal state is just a naturally mixed state, so like a very high temperature thermal state. So this general problem happens in general, but for the point of illustration, we'll consider this example here. Now, in this paper, they derived explicitly two pairs of catalysts, the rho cat naught and rho cat prime, which satisfy this relation here. So that this is their trace distance, where ds is the dimension of the system, and d cat is the dimension of the catalyst. So, but what they found is that for these particular catalysts, that the following is true: that you can go from, under thermal operations, you can go from any initial state to any final state. Or in other words, that the theory of thermodynamics has become completely trivial. So every transformation is allowed. Okay. And here, the important point to note, maybe, is that in this example, which can achieve this, the trace distance goes to 0 as the dimension of the catalyst goes to infinity. So even if the dimension of the catalyst gets very, very small, you can still, the theory can still become trivial. And this is the tricky issue with catalysts. So, yeah. Okay. Sorry. Yes. So I mean that so what I mean is that if we only allowed here exact catalysis, yeah. So the final state rho cat had to be the initial state, yeah. Then not all transformations are allowed. Okay. You can't and remember here this is under TO, right? Which I said this is very important that you get this. So it's nice that you asked the question. Okay, or maybe which are explained here, right? So or at least if you have a catalyst. So under these transformations, not all transformations from rho s to from the initial to the final allowed. Only a subset, because this is a non-trivial condition to be satisfied, right? But what I'm saying now is that and by that I mean it's a non-trivial theory that interesting things can happen. It's not that what's allowed to happen? Well, everything. No, I mean only very particular things can happen. However, in this example here, it turns out that if you allow for this inexact catalysis, then of this particular form. So in the paper they derived particular expressions for these catalysts. I didn't put them here because it's not so relevant. But they derived particular expressions where they prove that for those particular catalysts and this state, that every transformation is possible. So now there's no point in talking about any theory of anything, because it's just completely silly. And as I said, the important point here to note, though, I mean, the fact that such thing can happen is not so surprising, right? In the sense that, sure, if I allow for some some other system here, it makes sense I'll be able to transform. What is a bit maybe perhaps surprising is that this can happen even when the dimension of this catalyst goes to 0 in trace distance. So here you can have the fact, could you see it goes as log dcat. So as these catalysts become very, very large, it turns out that the trace distance can become 0, yet it can still become completely trivial. And it's not just, everything is allowed, okay? So this was in 2015. So yeah, so okay, so that's the point. And now, yeah?
I had a related question, just I guess about the notation with
Yeah.
the arrow, and then you have the tensor product on the right side.
Oh, this.
And you actually have to get a product state after the.
Yes, that's one of the conditions. Although I mean that I think okay. So this constraint comes from the definition of thermal operations for exact catalysis. So there you require that the catalyst product. So it's an interesting question whether or not. So other theories, other versions of thermodynamics have considered the case where you do not require this stringent constraint, but only locally you have catalysis. The argument from it, from a physical point of view, is that if you really want to use this catalyst, you really want it to stay product, because otherwise, if it becomes correlated, its use may be degraded. It's an ongoing debate. Some people argue, yeah, I think it really depends on the setting. If you had a fresh system, then yeah, it would be fun.
What about for this one with this inexact catalysis? Do they actually get product?
So here, yes. So here in this particular example in the paper, they do consider their version of inexact catalysis is when it's product. But a similar thing would happen even if you don't allow the product here. Okay, at least in principle, you could get this kind of scenario where you could, if anything, actually not having product would just make it easier, because now even more stuff is allowed, right? So that if you relax that, it would just be even easier to satisfy this. Okay, so basically the take-home message is that when you have these catalysts and you have inexact catalysis, potential issues can arise in the sense that you can make the theory trivial. Now, as I just showed in the previous slide, you can think of these control devices as actually inexact catalyst machines. So even if, as they become very large, even if they control the system to higher accuracy, even if their trace distance goes to 0, there's at least a possibility that you could actually be invertedly trivializing your theory by allowing for much more transformations to occur. Okay, so this is why you have to be careful. Okay, and there's something interesting to talk about. So now our first theorem is basically, before I go into the details, I'll just give the general message, is basically saying that what is the minimal, how good, what is the minimal, what is a minimal requirement on how good this control device is in the sense of trace distance of in terms of the error, how quickly this error has to go to 0, such that you can be guaranteed that you're not trivializing the theory, in the sense that really only the initial the same operations are allowed. You're not allowing for more operations, okay? In some sense, you can see it's similar to the previous result by them, but in a different direction. So now we really want to say that nothing extra is allowed, rather than everything is allowed. So explicitly, yeah, we can. The theorem goes like this. So imagine now you have some time independent Hamiltonian, which is over the system, the catalyst, the control device, and the thermal state. Okay. And the key here, okay, we have to work in the case where this is much mixed state, okay? And now we define this epsilon embed as being some quantity that satisfies this inequality, okay? So in other words, it's basically the difference between the actual final state you can actually achieve autonomously and the ideal case where you would have essentially exact catalysis of both the catalyst and the clock or control system. Okay, we also control the system state here, but this is not really so relevant because you could trace that out, and it's more about the catalyst. Is the important message here. So, and this is a measure of how quickly this error goes to 0 as you make the dimension of your control device larger. Okay, and generally speaking, the larger you, of course, the larger you make your control device, the more degrees of freedom you have. So the smaller you'll be able to make this. Okay, as a general rule of thumb. So now, given this definition in terms of this state, we proved that there exists some state on the system and some additional catalyst, such that this transformation is allowed under the, I put here noise operations, but these are these thermal operations under this setting. Okay, so we show that you can go to this state. So basically, this state is now a non-trivial. It's a non-trivial transformation of the theory, saying that this is what the theory should allow. But in the case of exact catalysis, and exactly the ideal case. So this state exists, and this state is a distance epsilon resolution away from the actual state of the system you achieve. Okay, and this epsilon resolution depends on this epsilon this epsilon embezzlement. Okay, and explicitly this part here is the actual important part. The meaningful part of the theorem, if you want. This equation that relates how quickly epsilon embezzlement has to go to 0 in order for epsilon res to go to 0. Because you can see now, so if we could achieve some control device such that this goes to 0 quick enough, such that epsilon res goes to 0, that would mean that simply that the final state we have is really is always going to be very, very close to something's allowed. So clearly it's not that we're allowing for extra stuff as we make the dimension loss. But that's only if this this goes to 0. Okay. So I mean, these are not from explicit clock constructions, but just for a point of argument. So if, for example, this goes to 0 only as some inverse power law, then this would not be good enough, because if you put this in here, as you make the dimension of the clock very large, it doesn't go to 0, right? Because we have the log on the top. So it wouldn't be good enough. However, if it was exponentially small, then it would be good enough, and we could really prove that yes, whatever this clock is really doing, it can't be allowing for more transformations. But these are just some examples. I haven't said whether or not such a clock system can exist that satisfies this. Yeah, it's just to get the point. Okay, so now basically I will show a particular clock construction which does allow for this exponential decay of the error, and so that everything, at least for this particular construction, you can be guaranteed that whatever the clock is doing, everything is fine. So this is known as the quasi-ideal clock, which is a paper I have with co-authors Ralph Silver and Jonathan Ottenheim. Yes. So anyway, and basically how we define this is that it has some free Hamiltonian, okay, H clock, which is some truncated harmonic oscillator of equally spaced levels of dimension d clock. And the initial state is a pure state of this form. So this is just a sum over the d integers centered around this value k0 of this expression here, where these amplitudes we're sampling from this complex Gaussian distribution. Okay, and the basis it's in is the discrete Fourier transform basis of the energy eigenbasis. Okay. So this defines a particular control. This is the initial control device, and it's Hamiltonian. So, in this setting, you can define a potential term, which is given in terms of this function v0, which is some periodic function, and it's diagonal in the Fourier transform basis of the energy basis. Okay. Now, given these things, what we proved in this paper is that the dynamics under this joint Hamiltonian on the clock or control device has the following expression. So what you do is you take this initial complex Gaussian and you shift it in time to a later point, and you resample it. Okay, and then you multiply by a phase, which is an integral that depends on time over the potential. Okay, and this is true. This is the ideal case, if you want, where it's just translation, so some translation in space, and it has that behavior up to some correction term. Okay, and now the key point is that the correction term up to some polynomial correction grows linearly in time and is exponentially small in the dimension up to, and depends on this correction term, which I don't want to go into details in this talk, but this depends on the potential and how steep it is essentially. Okay, so given this, what our result 2 is now, we take this clock model and we calculate the epsilon embezzlement for this particular clock model, and what we find is that for all times t before the unitary is applied and after the unitary is applied, that we can prove that the epsilon embezzlement grows polynomially in the dimension of the system in the cat, but is exponentially small in the dimension of the control device. Okay. So as a consequence of this and the previous theorem, it tells you that for all times before and after the unitary has been applied, that really epsilon resolution goes to 0. So really, if you use this clock, no matter the exact details of what it's doing, you'll be guaranteed that you're not increasing the allowed operations of this theory, and it really is then the laws of exact catalysis up to some small correction term. Okay, you're not trivializing the theory, and now it's become autonomous as well. So you may wonder as well, like, but also how does this result depends on these 2 times? Well, this constant here depends on these times, on this t1, t2, and in such a way that as this constant goes to 0 when t1 approaches t2. What that's saying physically is that if you try and do this unitary arbitrarily quickly in a small and small amount of time, then it also breaks down and it doesn't become autonomous anymore. Okay, so there's I won't go into the exact details of the dependence on this function, but for all constants it's exponentially k. Okay, so and just to highlight why this is also non-trivial is that there are other examples of clock models in the literature, namely, for example, the Salica-Wigner-Perez clock, where you can show that the epsilon embezzlement goes as 1 over poly d, case, for which this epsilon resolution goes to infinity. It doesn't go to 0. So here it's an open question to whether or not this would trivialize the theory or not. Because I mean, it could be that our bounds are simply not good enough, or it could be really that it doesn't trivializes the theory. Okay, so now said that, I will define. I will add more structure to the model. So I'll give more structure to the type of the Hamiltonian and prove that if we assume more structure, we can get a much tighter result, but it also has some caveats to that from a physical viewpoint. So for that we make this, we define the embezzlement-free control model, which basically has Hamiltonian of this form, where the time-independent Hamiltonian on the system catalyst, thermal state, and control device is of this form here. So it's just some local Hamiltonian on the part to be controlled via the clock, times some interaction term on the part to be controlled by the clock, and some interaction term on the clock that makes the interaction non-trivial, tends to some free Hamiltonian of the clock. Okay, and this is also in this model. This is what we call the free Hamiltonian of the clock, which would, in the ideal world, would be the evolution of the clock would only be given by this guy. Okay, so now and this obviously satisfies some conditions that these terms commute, and this condition too is the really kind of important condition that we demand, that this int term satisfies this relation here, CIP here, for some rho s, rho cat, and thermal state. Okay, so if it satisfies this condition, then what we can prove is the following, actually, that we can define this embezzlement term prime via this relationship here, so it's very similar to before in the sense that it's saying, this is the actual dynamics you achieve according to the free evolution of this time-independent Hamiltonian versus some ideal, the ideal evolution of the catalyst and the ideal state you would get for the control in the catalyst, and this is some ideal switch where it goes from the initial state to the final state after these times. So if you define this epsilon like this, then it turns out there exists another catalyst state such that this transformation is again allowed by thermal operations in general. So basically what this is saying is that the epsilon resolution this time is equal to the epsilon embezzlement, okay? Right, so now all we require in this model to be able to say that you're not cheating something, you're not extending the rules of what you can do, is that the epsilon embezzlement is equal. So we only care that epsilon embezzlement goes to 0, but it could go to 0 very slowly, and now everything is fine. However, what you see here, in some sense what we're doing in this model, is we're hiding the dynamical complexity of how accurate the dynamics can be to this ideal case, and how accurately it can manipulate the catalyst. We're hiding all that into the Hamiltonian, the preparation, because now we're demanding that this Hamiltonian has this very, very special structure where essentially it has this term that can perform exact catalysis. So you could imagine maybe from a point of view of constructing this initial Hamiltonian, this could be potentially problematic, because now as the dimension of this catalyst gets larger, you would have to prepare to very, very, very high accuracy your Hamiltonian in state in order not to be able to cheat here. So it's kind of pushing the problem from the dynamical setting to the initial Hamiltonian preparation. Okay, so in terms of conclusions, what we asked was, is it possible in the resource theory or quantum information theory approach to thermodynamics make this unitary, which is ubiquitous to all protocols, if you want, autonomous and free. So as I said, it was already free, but it wasn't autonomous. So now we want to combine the two. And what we've shown is that yes, you can, although there are many subtleties and many open questions one could ask. We've also, in doing so, we've also come up with a way to understand what does it mean, how to quantify the cost in the thermodynamic sense of this control. Namely, we've shown that this autonomous control can be thought of as a clock and as inexact catalysis, which is kind of the important part here, because now one can take all the tools from inexact catalysis and trying to apply them to this problem, taking into account that now it's really dynamical though, and you really have these extra constraints that the time-dependent Hamiltonian. So that's basically what we've done. And then, of course, there are many open questions. This is just a small subsection. One question is that it was known in inexact catalysis that if you have the trace distance between the exact and inexact catalysis goes 1 over log of the dimension of the catalyst, then everything becomes trivial, everything's allowed. On the other hand, what we've proven now is that if it's exponentially small, or approximately speaking, exponentially small in the dimension of the catalyst, now nothing in addition is allowed. So yeah, so it's 10 minutes, yeah. Okay, so these are basically at the opposite ends of the spectrum. Okay, so it will be interesting to know whether these are both tight, or whether or not one can actually do better, and also is there some intermediate regime, or like is an intermediate scaling where if this is say 1 over poly d, which is in between the two, then or something else, do you get a scenario where more operations are allowed than simply in thermal operations or catalytic thermal operations, but not everything is allowed. So it's still non-trivial, but not as restricted as the standard theory. Another very interesting question here would be, what about classical versus quantum control? So what I mean by this is, if you've seen, we've considered this auxiliary system that's controlling the system fully quantum, right? We didn't put any restrictions. And it turned out that if we don't assume some like extra structure, that the only way that we proved that that we needed this clock that was very, very good in the sense that it was really just an exponentially small error. Okay. Now this quasi-ideal clock model that we used that does this is an extremely quantum mechanical object in the sense that it's really the basis uses the discrete Fourier transform. It's highly coherent, and it really works so well because of destructive interference in the dynamics can really see this. So if you were to take that model and now demand that it was always diagonal on some basis as it evolves, so it was like stochastic, in other words, yeah, then I don't believe you could get it to be exponentially small. So it really seems that there's this quantum advantage here, and that's an interesting question. You know, what is the difference? Is there some sense in where you need quantum control to make these operations work, or is that not the case? And then, of course, another thing is that you could go beyond the single shot limit. So in some sense, what this talk is about being about the single shot limit, where we talk about applying one unit and, you know, can you do it autonomously? And we've started from there. We haven't, you know, but you could now ask, what about if, because, you know, in real protocols you don't want to do one unit, maybe you want to do many, you know, in sequence or something, in like a quantum heat engine, right, where you apply different unities for different strokes. So so here you would then you would want to know how this now scales with n, you know, because now the additional errors would add up if you want. So that's another interesting question. So yeah, and this is just some selection. Of course, another interesting question would be at the moment that this theorem we have here is only for the special case where we assume the bath to be very high temperature or maximally mixed, okay, which is a very kind of particular case of the general theory. So it'd be nice if we can generalize that to the more general case. So I guess I have five minutes, so I can just briefly, maybe, okay, I could talk about that a little bit more, but maybe it's more interesting to open up to questions over 5 minutes. Probably questions are more interesting than me just talking. So, yeah. Or we can all just go for lunch.
Well, since you're asking this, so if you control the minimum eigenvalue instead of the maximally mixed state, you would still be able to do this. So
okay. So yeah, okay. You wanted me to explain what I was talking about. So yeah. So in the case of really full thermal operations, in the case of in the case of the first theory where you prove exponentially decay, but only for maximally mixed state. So how could we generalize those results to thermal operations? So here there are some technical points that you can see, which means it will be definitely non-trivial, and in the following sense. So it's known. There's this paper by Markus Müller and I think one of his PhD students, I forget the name, called Quantum's Horn's lemma, I think, or Horn or something like this, lemma. Which and there what they prove is that it turns out that in this special case of these what's known as noisy operations, or you know, in the case where the thermal state is maximally mixed, you can do all possible transformations with a finite bath, okay, with a finite dimensional system, and that's actually quite useful because if you think, as you've seen before, the errors tend to scale as on the control system. They get larger if you make the system to be controlled larger, which is somehow intuitive, right? The larger the fish you want to control, the more back reaction you'll suffer. So it was kind of, it didn't appear, I think it appeared indirectly in the maths that the fact it was finite dimensional made things much easier, because basically it means you have to deal, that I didn't go into detail the proof, but we dealt with Renyi bounding or getting continuity bounds for Renyi entropies, whereas had we had the full-blown theory with general thermal states, we would have to apply those Renyi entropies for Renyi divergences and have to get continuity relations for Renyi divergences. Now, so basically, though, in the more general case, in this Horn's quantum lemma, in this paper by Markus Müller and Korfus, what they also prove is that in the case of thermal operations, it turns out that there are certain transformations that you can do only in the limit of infinite dimensional baths. And so it means that the mathematical machinery that we would use in the proof automatically, if you want, it has built in there the possibility of this bath being infinite. And that's reflected in the maths in the sense that when we try to derive uniform in alpha continuity relations for Renyi divergences rather than Renyi entropies, they behave really badly. They have really bad scalings. And I think this is a direct manifest of that point there. Actually, maybe one could use that, and it turns out that it seems that you would need a clock that has an error that's precisely better than exponential decay. Anything that's better. So any e to the minus f of d, where f of d grows quicker, more than linear, would have been good enough. But it's precisely the best clock we can do is exactly exponential. It's nothing more. And I don't think that's a coincidence somehow. However, that said, this you can also see as maybe perhaps more of a technicality, in the sense that rather than taking all thermal operations, you could take a dense subset of thermal operations where you only allow for the ones that have precisely a finite dimensional bath, which will be a dense subset of all the allowed operations. And here, of course, now you no longer have that problem. Now, the technical difficulty in then proving that is we can't use all these relations, the if and only if conditions for state convergence under any alpha divergences, because I have that programmed in. But perhaps that's not a problem because, I mean, there's a now work in progress. One could maybe there's a way to embed thermal operations in terms of these noisy operations, and then you can work with any entropies rather than any divergences. And that's a way perhaps to get around this this problem. That's something like Mischa and I are doing, like trying to generalize still. But because it's technicality, it's not more complicated. Yeah. But that would definitely be very interesting. Did that answer your question more or less, or was it?
More or less.
Yeah. Okay. Good.
Okay. Maybe one more question. Yes.
So to apply an energy conserving unitary, in principle you can turn on your Hamiltonian adiabatically very slowly and then turn it off adiabatically again in an infinitely long time.
Yes.
So it means that, I mean, in principle the resource of clock that you need can be arbitrary, become arbitrary negligible if you go to this adiabatic limit. Have you looked at
maybe, yeah. It sounds
between the total time that you need to implement your unitary and the resource that you need to.
That's a very good thing. That's a very good question. So that I suspect, I can't say for sure, but I suspect you're right. I mean, I would tend to agree with that, at least on the intuitive point of view. So here, when we derived all the theorems, basically we just assumed that it was some fixed time interval, T1, T2, where we just say before it's not applied and after it is. But where we saw this is something I briefly said in the talk, that this epsilon beta, we said that this term for this quasi-ideal clock is exponentially small, right? So when I say it's exponentially small, it has this constant out the front that has to be non-zero, right? It has to be positive in order for this to be exponentially small, right? So. But this constant depended on these times here. So if in the limit where, it's kind of a bit related to what you're saying. I'm saying like if you take the limit where you do it arbitrarily quickly, then all this breaks down anyway. So you'd have, but I guess in the opposite limit, it will maybe become trivial as well in some way. You could get, I guess in the opposite limit, if you scaled the time difference with the dimension of the clock, so as you say that as I make the clock larger, I'm allowed to take longer and longer, then of course this is now super exponential decay. Oh, actually that's a good point. And now I could actually easily solve for the more general problem. But somehow that's again cheating. Well, cheating in the sense that you really want to do things in finite time, right? You don't want to take infinite time. So you have to be careful. It's a subtlety of limits now. You know, limits don't commute, etc. So you have to be careful. Having said that, one potential application of this work, which would also be very nice, is also, for example, looking at something that's a hot topic at the moment is the third law, right? That tells us how quickly we can call. Now, so in some sense, you can see there's two aspects of this. There's the one, even if you're allowed to apply after unitaries, depend on the size, you know, in arbitrary time, depend on the size, you can get a third law in the sense of as a function of the size, but not a function of time. Results like this, in some sense, would allow you to get a third law, but as a function of time, because you could say, you know, without destroying the catalyst, how quickly can I do it, right? How quickly could you call? So you could even investigate if you want the other aspect of the third law, which hasn't really been understood in a resource theory. The first aspect has, but not the second aspect. Yeah.
Okay, so let's thank the speaker again.